Okay, so no problem if you really don't understand, just stop me. Okay, and there are a few things that you're supposed to know is molecular orbital theory. So if you have the time, you need to read back, which is quite difficult. Molecular orbital theory is actually a first year subject of chemistry where you learn about covalent bond, okay, where the electron is in the orbital. Okay, and it's not important for exam whatsoever, but it is important for you to understand the fundamental of how it works. Okay, so this molecular orbital theory will give you the idea of how the machine's actually running. Okay, you probably send samples to these machines and you get the reading. It's not really important for you to know the fundamental, but at least give you some idea. Okay, all right. So the first that we will cover is the theory, and please do. There's a lot of YouTube videos that you can go through to understand molecular orbital theory, and they are very what we call uh, animated, so it's quite easy for you to understand. Yeah. All right. So the first objective. So as I mentioned, this spectroscopy technique, atomic spectroscopy technique, they have three types. Okay, I will tell you why. What is the meaning when we say absorption, fluorescence, and emission? It is based on how we read the output of the measurement. That's why we have absorption, fluorescence, and emission. Okay, so one keyword is atom. Okay, meaning that the metal that we analyze will be in atomic form. It's not molecule, it's not ion, but will be in atomic form. Okay. Okay, so this is molecular orbital. Okay. All right. So what you need to understand from this slide, okay, if a molecule, okay, or if metal, okay, uh, is excited, okay, they receive energy. So it's a simple idea. Atoms or molecules receive energy, they will be excited. Okay, so this is the ground state, meaning that this is the original energy of the molecule or the atom. Okay, and then if we provide certain amount of energy to the atom or the molecule, okay, the molecule or the atom will be excited. Okay, so for the concept of molecular orbital, okay, there is what we call as highest occupied molecular orbital. You can see it is occupied. So this represents electron in the atom as well as in the molecule. So you can see, I hope that you still remember electron spin, spin number, okay? So this is lowest unoccupied. And U stands for unoccupied molecular orbital, because why? You can see based on this level of energy, this one is of course the highest energy. Yeah, you can see based on the scale here. Going up, this orbital has highest energy. So when the atom and molecule receive energy, okay, specific amount of energy, it will be excited. So you can see that um, the excitation, okay, you might have from here, okay, you can see, let's say the molecular atom energy is here, pi, it can be excited to pi star, or from n which is here, it can be excited to sigma. This is called sigma star. And all this, of course, this is the highest, meaning that in order for this from sigma energy to sigma star energy, the excitation requires a lot of energy, and this usually does not happen. Okay, and the most common that happens is from n to pi star. Okay, from n, because if you look at the gap, this is the smallest gap. Okay, so what I'm trying to tell you here is what happened in the machines. Okay, what happened in the machines? The atom will be excited, and there is a electron excitation. Okay, electron excitation to a certain level of energy. But in order to discuss you in detail, so this is not covered under this topic. Okay, so it's not that difficult. You can revise back on molecular orbital. But the concept of excitation for molecule and atom is important for you to have the idea of how the machine works. Okay, right? It's okay. If you don't understand, you can ask me again. Yeah? Okay. So this is schematic. Okay, just now is at orbital level. The excitation of atoms and molecule triggers the excitation of the electron inside molecules and atoms. But in order for you to understand easier, this is what happened. If you provide a certain energy in the form of light, we bombard laser, we bombard UV, we bombard visible region to the molecules or the atoms. Okay, so we can imagine that the electron excited just now. Okay, it gets excited, it moves to higher energy level. It's all about energy. It moves to higher energy level. So what happened to the electron after that? Okay. What happened once it is excited to higher energy level? It will not stay there because it is unstable. Okay, just like when we go to a higher level, we need to go down, yeah, because it's not stable to be on a higher state energy. So what happened is uh, the molecule and atom absorb energy. So the electron is excited to the higher level energy, but it has to come down as well. And when the electron goes back to lower energy, okay, it will emit certain light also in the form of energy. So let's say if the electron uh, move from here to here, it will also emit the same amount of energy. Okay, but this also does not happen every time. Okay, it might be releasing or emit lower amounts of energy. Okay, so first, what you need to understand is there is absorption of energy, which results in excitation of the atom and molecule, and the electron is excited to higher energy level. Okay, and then what we call as the second process is relaxation. It goes back to lower energy, and during the process, emission of light happen. So absorption, excitation, and emission. Okay, so this is the fundamental that happens in the machine. Absorption, excitation, and emission. Okay. Okay, I'm not going to discuss this because fluorescence is a bit different than absorption. We focus on absorption first. Okay, focus on absorption first. All right. So this is the machines. Okay, the schematic of how the AAS the technique is known as atomic spectroscopy, but the machine is known as atomic absorption spectrophotometer. That's the name of the machine, not the technique. The technique is atomic spectroscopy. So you can see here, these are the main parts. So we will learn about the hollow cathode lamp, what is the function, and then this is atomizer, and then we have monochromator and detector. So this is where the sample that you will be submitting into the machines. So this is the basic. If you have a very good AAS, probably an expensive one, probably they have a better additional. That one is the engineering part of it. But these are all the basic that needs to be in the EAS. We call it EAS. Yeah. So the machines look like basically looks like this. Okay. Sorry about my okay. So this is the hollow cathode lamp. Yeah. So in AS, okay, the hollow cathode lamp, you need to provide. Let's say you want to analyze plumbum. Okay, let's say, or you want to analyze chromium. You have to provide specific lamp for chromium. You have to provide specific lamp for plumbum. So it is different, okay? Because it will bombard with different wavelength, with different amount of energy. Specifically for plumbum, for example, specifically for chromium. So you have, if you want to run AS, you have to check with the service provider. Are they can analyze that particular metal because it requires specific lamp for each metal. Okay, so this is the hollow cathode lamp. Okay, yeah, this is the hollow cathode lamp. And this is the atomizer or flame. Okay, we will discuss the function of each of these parts after this. And this is what we call as nebulizer. Yeah, this is the sample solution, and then you have the nebulizer. So inside here, we have nebulizer. So this is the basic of AES. So each of these uh, parts, they are very important for AES. And this is how the sample is being delivered to the machines. Yeah? So if you look at sample that is provided, okay, right? So once the sample goes into the machines, it will be nebulized, means that it will become small, what do you call? It's not vapor, but it's small liquids.
Small droplets.
Yeah, droplets, okay? That's why it is called nebulizer. So it becomes small droplets of liquids and aerosols. Sometimes we want it to be as fine as we can because from here it will be subjected to bombardment of energy. So you can see that this is the energy is bombarded by the hollow cathode lamp. Okay, so the sample nebulized, and then this specific hollow cathode lamp will bombard the um, the nebulized sample with specific amount of energy. So remember about the one that we talked just now. The molecule will be excited. Yeah, the molecule will be excited based on amount of energy provided. Okay, that's why for AAS, it has to be specific um, lamp, okay, collocated lamp for a specific element. Yeah, you cannot do all the elements at one time. Now, first step is of course molecule, but the molecule has to be dissociated to become atom, because this is atomic absorption spectroscopy. So the measurement is based on atom. So it has to be dissociated from molecule form into atomic form. Okay. And now you have excited atoms. Okay. So the one that we measure with the EAS is the excited atom. We don't do excited molecules and we don't do excited ions. For AAS is excited atoms. Yeah. But of course, the process we also cover. Sometimes we have some uh, problem, which is we have ions as well, or some molecules that is not dissociated. So this will contribute to some errors. So that's why the process of atomization, okay, meaning that to produce atoms, is very crucial in EAS. So which part that atomize is the flame. So you saw the flame just now. So this is the one that atomize, break down the molecule into atoms. Okay, so if we don't have enough power of flame, you have molecules, then your reading will not be accurate. Okay, so this is EAS. So this is the example of the fuel used for the flame. So it is acetylene. And then we need, of course, oxidant to just to burn the molecule. Yeah. So this is again the process. Okay, the same process that I have shown just now. And even the combustion flame, the flame also have certain region. And of course, this is where the most important interzonal region, because we have high concentration of free atoms, because we need atoms to be analyzed. We don't want any other like molecules or ions, but we need atoms to be analyzed. Yeah. So the efficiency of the flame is very important in AAS. Okay. So these are some guides. If you use like air, hydrogen, and acetylene, as you can see, acetylene provide the highest temperature to burn the molecule or to dissociate the molecules into atoms. Yeah? Now, this is a very specific region for flame structure. So you can see that if you have like, you want to analyze chromium, then the region of the flame will be different. Okay? Of course, you don't have to memorize all this. This is not the stage that you need to memorize. Disadvantages, there are some disadvantages if you use flame to atomize. You only 5 to 50% of the nebulized sample reaches the flame. Probably the droplets does not efficient enough to reach the flame to be atomized, and it requires quite a lot of samples, like 0.5 to 1 mil, to have a good reading. So if you have very limited samples, then using flame atomizer is probably a not good option. And also, if you have a very viscous samples, you have to do some pre-treatment, okay, to make sure that your samples are clean, um, thin enough for the nebulization process to happen, and the atomization as well. So sample preparation is very important for you to take note. It has to be clean, it has to be filtered, it cannot be raw samples to be submitted to the EAS. Okay. Now, okay, so this is the one that we talk about is flame. So there are other technique like electrothermal and plasma. Okay, so this is the sources of heat to atomize the molecule, right? Right. So remember about the technique of reading: first absorption, emission, and fluorescent. Okay, we haven't discussed about fluorescent. Okay, let's go back to the first basic slide. Okay. Okay. So remember about this when I mentioned absorption and then excitation happen. Okay, absorption provided by the hollow cathode lamp, and then excitation of the molecule, okay, atoms, and then of course all those process atomization whatnot happen, and then after it has to be uh, it has to go down to um, stable energy level, and that's why we have emission of light. So that's why we have three types of how the machine reads. Okay, that depends on the detector of the machines. So the machine can read absorption, the machine can read emission. Okay, so it depends on the machine. If it is reading absorption, then we call it atomic absorption spectroscopy. All right. So if it is reading, the detector reads emission, then it is emission spectroscopy. That's why we have three. And one more is called fluorescent. Okay, so fluorescent is a bit different. So let us talk about fluorescent before we move on to the the next one. Okay. So this is yeah, a bit complicated, looks like, but it is the same principle. So remember that the the molecule or atom receive energy absorption. It gets excited. Okay, the electron gets excited. If it is 100% relaxation, you can see that it goes back to the ground state. But for fluorescence, okay, this is what we call, you can search Jablonski diagram. So what is fluorescent? Instead of having the electron goes back to ground state and emits energy, there are other processes happen. One is what we call as internal conversion, vibrational relaxation. They are mini processor, I would call it a mini processors, and it might have inter-system crossing. And you can see that after, instead of just going down straight to the ground level and emit the energy, just like the diagram that I've shown just now, it undergoes internal conversion and vibrational relaxation, and it goes down, of course, but you can the energy emitted now, the purple one, is not the same as it is that it absorbed in the beginning. You can see that the gap here and the gap here is not similar due to this process. And this produce fluorescent. Okay, and this happens. It might happen to certain molecules. Okay, it doesn't happen. I don't think it happened to metals, but it might happen to organic molecules like this. Here, let me show you. Okay. Okay, so this is what we call as conjugates. You have electron in double bond. Okay, so they have this characteristic of chromophore. We call it as chromophore. So it might contribute to where is me? It might contribute to this process. Okay, instead of uh, straight clean go back to ground state, it has additional process and does not have the same emission value. So this is what we call as fluorescent. Phosphorescent, let me put it away from you. So fluorescent, because for phosphorescent, there is additional called intersystem crossing. So we don't want to discuss this, but at least you know absorption, fluorescent, and emission. these three that you can use for atomic spectroscopy. Okay, so meaning that depends on the machine, whether the machine has the capacity to measure absorption, then you get the reading of absorption. If the machine measure fluorescence, then you get the reading of fluorescence. And if the machine measure emission, then you get the reading of emission, but all are usable. And when we talk about fluorescence, one thing about fluorescence, it is very sensitive. So if we have a very low concentration, okay, of certain molecules, organic molecules, then probably fluorescence is the best choice. But we do not usually have that in lab. Usually what we have is atomic absorption spectroscopy or atomic emission spectroscopy, absorption spectroscopy or emission spectroscopy. It's quite rare to have fluorescence. Okay, all right. So fluorescence is very sensitive, but very rare that we have fluorescence for spectroscopy, for metal analysis. Okay, now, so this is the basic. Right. So the third part that I haven't discussed is monochromator. Okay. This is monochromator because we have discussed about sample introduced into nebulizer to have those droplets. And then this is the energy provider. Okay. And then the molecules and atoms will be excited, and this one will be atomizer to separate the molecules into atom. But we haven't talked about monochromator and detector. So this is where when I say it's either the detector will be detecting absorption or the emission or fluorescent. So that depends on what the detector will be recording. Okay. And the monochromator, what's the function is to narrow down the wavelength that the detector will be detecting. So let's look at how it works. Where is the okay? This is detail of the. Let me. We will be coming back to that. So monochromators are designed for spectral scanning, right? Uh, it will narrow down so that we have specific reading for specific uh, element. Yeah. So I think, all right, this is how it works. Okay, so you have a very specific lambda. If it is absorption, if it is emission. So I'm not going to discuss the engineering part, yeah? But this is how it works. All right, so let us detail a bit on the light source. So this is the hollow cathode lamp. So since you have this word cathode, and what's inside the hollow cathode lamp is it might be neon gas or argon. So what happened here is, so if you provide, um, if the metal is excited by, this is how the metal is excited. Yeah, the lamp is filled with inert gas like argon. So this argon will, when the energy is provided, the first being excited is the argon gas. Okay, and this argon gas will sputter off the metal. So the next process is you can see that the metal or the atom just now will be excited. That's why you have M star. Okay, excited into higher energy. And once the excited state returns back to the ground state, it emit certain energy. Now I see that you start scratching your head. Okay, this is the detail of hollow cathode lamp. So inside hollow cathode lamp, there is inert gas, argon, or it might be neon. And when the energy is provided, it's not straight away to the metal, but it will excite the argon gas first, and the argon will excite the atoms, the metal atoms that you are analyzing. So you can see this is solid, and then become gas, and then then you have excited metal here. Yeah, this is the detail inside the hollow cathode lamp. So we have discussed a monochromator that will filter the wavelength before it is recorded. A lot of jargons here. And then the last part will be detector. So detector, there are different types of detector. As I mentioned, if it is absorption, then you have absorption. If it is emission, then it will be suitable for emission. And then fluorescent. Okay. So, well, you don't have to memorize all this. But the most important is to understand the principle of how AS is working. Okay. Atomic spectroscopy is working. Okay. So before we move on to the second one, first is fundamental of the absorption, excitation, and emission. And then we have absorption and fluorescent emission. And the second part is the, um, let's look at the learning objective. Okay. Theory, okay, and then schematic diagram of instrumentation, like we have hollow cathode lamp, we have nebulizer, we have atomizer, monochromator, and detector. Okay, so those are must have in atomic spectroscopy. Okay, and then so we have discussed all this. Okay, so let's go to the emission part. Yeah. So remember about the flame just now. Okay, the atomizer based on flame. So this is another example of, instead of using flame, we can use plasma. So plasma is actually very high heat. Okay, it contains gas like argon, yeah, that is heat up into very high energy. So this will provide plasma, and this will do the job for atomizing the molecules. So you can choose this or you can choose the flame. But this one is of course much better because it is more efficient for atomization process, but it is more expensive than the flame. Yeah. So it is called plasma. The usage is similar to the flame, is for atomization, yeah, to break down the molecules. So this is how it looks. Uh, this is how the process of plasma being produced. You have induction coil. So this is where the plasma region means that this is the hot region, okay? And the function is similar. So this is the nebulized sample in aerosol form, and it will be atomized here. As long as you have heat, you can atomize a molecule. Okay, so the function is similar for atomization, but now instead of using flame, we use plasma. Okay, all right? Okay. I'm just providing you some of the, I will be providing you tutorial questions, so don't worry. So we can discuss, like, this is a question, similarities and differences between AAS. AAS stands for atomic absorption spectroscopy and atomic emission spectroscopy. for mineral. So I believe that this is what you want, right? For mineral analysis. So if you can look at what we have discussed, and you probably can think about what to answer the question. Okay, the keyword, of course, we have absorption and you have emission. And this is postgraduate. This is no longer undergraduate. I mean, you are free to search resources to understand better. Okay, so this is not something that you have to restrict yourself like undergraduates. There are so many resources that you can search, right? Okay, so this is the model answer used to quantitate elements. This is the similarities of AES and AES. Okay. The problem we will discuss after this is on interferences. Okay, sample preparation. Okay, the differences. AES is based on atom absorbing energy, but AES is atoms emitting energy. The word is emit. Okay, and energy from hollow cathode lamp. Okay, AES is using hollow cathode lamp, but AES is the one that is being measured is heat energy from flame. The flame used to atomize, okay, and the emitted one is measured by the detector. Okay, so that is the biggest difference between absorption, AES, atomic emission spectroscopy. So you can detail out, you can read more detail. Right. So before I proceed to just a bit more on AES and AES, do you have any questions? Just take some time. We can take a break around 5 minutes.
Okay.
Hmm.
Uh, for the hollow cathode lamp, so it is not like a spectrophotometer to change the wavelength, not adjustable.
Specific.
You you need
Specific.
to change the whole hollow cathode lamp.
You need to buy.
Okay, for each element.
Yes.
Mhm.
So you have to, let's say, if you want to send samples to any service provider, you have to ask them whether they can do analysis for that particular element. Okay, so if they have the lab, then it's okay. All right.
Okay,
Usually they don't do mercury. If you are um, if you are doing analysis on mercury, usually they don't do. Okay, so think about more questions while I'm opening the second slide.
okay.
All
For the sample preparation,
right.
which solvent normally to be used? Is it depending on the machine or depend on the sample?
Okay. Usually, when we do, if it is metal analysis, yeah, if it is metal analysis, you don't use organic solvent. It has to be usually aqueous. Okay. That also depends on the service provider because they have the manual for that machines. So you have to consult them what kind of solvent, what kind of preparations is needed. So as I mentioned earlier, the structure of the machines depends on the model. Okay, now that we have probably better model that you can, it is more robust probably, that you can, it can be, you don't have to prepare a very good sample. It can be like more raw, okay? But you have to ask the service provider what kind of sample that you can submit to them. But I believe that it has to be clear samples, meaning that you have to filter, it cannot be dirty, because anything related to optical, yeah, we're talking about optical technique, which is absorption, emission, fluorescent, the sample has to be very clear. Because if there is any interference, like if you have solids, some solid particles in that sample, that it will interfere with your reading. Okay, so sample preparation, meaning that you have to If you're, let's say, if you are analyzing vegetables, then you have to do some crushing, filtering, let's say that's that kind of thing. But the solvent, you have to ask the service provider what is their limitations of the machines. Yeah. Okay. Right.
Okay.
Yeah.
Uh,
Yeah. Right.
One more question, Prof. So for the AAS, the principle is to calculate the amount of energy which is absorbed by the atoms, right?
Yes, it is based on that.
Mhm.
But
Okay.
you don't see the calculation. You don't have to calculate. It is auto calculated for you. Okay, so it's not for you to worry about that because once you receive the results, it will be in concentration form. So you don't have to do calibration or whatnot. That is not required.
All machine calculating.
Yes. Okay.
Okay, thank you, Prof.
All right. Okay, let me open the second one, which is on the possibility of interference, because every machine has this issue. Let me open. Oh, what happened? Okay, just a moment. Okay. So this is the second part. Before we end, we don't need to do like 2 or 3 hours. uh, Next week will be ICP. I will explain about ICP because my part will be on atomic spectroscopy plus ICP. The rest will be covered by Dr. Bimo. And you can always refer to these books. This is that we refer to, Skook or any other instrumental analytical methods that you have or you can get from the library. Okay? So the issue with any machines is about interference. Okay. So what is interference is in inaccuracy in reading. Okay. So that affect uh, the measurement that you get. Let's say if you run, then you prepare a different sets, but you have prepared the same replicates of different sets. And when you run and you have different readings, so that means that something wrong somewhere with the machines or with the preparation of samples. So I would advise if you are to send samples, please do replicates. Please do replicates because you don't know uh, whether you get a good one or you might have some interference issues during the measurements. So if you have a very not to say accurate, what we call as precise reading, then uh, you can start to calculate based on the standard deviation. If you have a good standard deviation, then it's okay. So what contributes to interference? There are two types. Just more. That might contribute to your reading. It is called spectral interference, and the other one is a chemical interference. So spectral interference is about the line overlapping, okay, and then broadband absorption. So you have to imagine a bit. Imagine the process that we talked just now is about excitation of electron. So we know all elements have different electron configuration. Okay, So all element has their own atomic spectrum, sorry. So like if you are to analyze manganese, it has specific atomic spectrum because it has specific electron configuration. So if you are to analyze, let's say chromium, you have chromium 6, chromium 3, they have different electron configuration. So the specificity of the analysis depends on the atomic spectrum. So because I'm not teaching you about atomic spectrum, because atomic spectrum, if you search after this, you will find it has spectral line. So each has unique trend, has unique uh, specific spectrum for each element. So sometimes these lines overlapped between the elements, even though you have specific hollow cathode lamp, but in a real sample, you have a mixture of metals. Okay, when you have a mixture of metals, because you cannot control what is the mixture of samples or elements in that samples, sometimes they overlap. Okay, so when they overlap, uh, there is a possibility that it will interfere with the reading. Okay, so that's why we have the first one is spectral line interferences because of the mixing of the different elements in that sample. The other one is scattering. We will look at what is the meaning of scattering and broadband absorption. Okay. The second one that contribute to interference is chemical interference. Okay. Formation of compounds of low volatility. Because when we submit the sample to the system, it has to be nebulized and it has to be in aerosol form before it can vaporize and form atoms. But certain samples, because probably it is too viscous or it contains some other compounds that has low volatility. So probably that compound volatile first instead of the main element that you wish to analyze. So it will also interfere because it's all about energy. This compound might absorb energy and lower down temperature. So that's why when we took the sample preparation is very, very crucial. Yeah, so you need to know at least some background of what sample you have. What are other contaminants that probably exist in that sample? Okay. Another one is ions, because in this atomic spectroscopy, we focus on atoms. So we do not want ions to interfere. Okay. So spectral interference, if you can open, apart from this, is look at the uh, spectrum for each elements that of your interest. You can see that the spectral lines. So this inside the samples, there are many other elements, and each element has their own spectrum. Okay, so and they are with different electron configurations, and you have to think about they might be overlapping lines. So if I talk about lines, you probably cannot imagine. So I would like to recommend you to open up spectrum, atomic spectrum. Let's say one example, atomic spectrum for mercury, atomic spectrum for chromium, then you will understand what I'm talking about. It is consists of lines, and it is very unique. It's like our fingerprint. So fingerprint for element is their spectrum, optical spectrum for each element. So it's like our thumbprint. It's unique for that element. And since we have a lot of elements in one sample, so there are probably some overlapping. But it is stated here, it's quite rare since atomic lines are very narrow, but it happens, okay? So the easiest way to overcome this problem is to choose another wavelength. So, for example, if vanadium absorbs at certain Armstrong, this is a wavelength which interfere with an analysis based on aluminum absorption. So we can adjust. That's why we need monochromator because the monochromator is to narrow down the wavelength that the detector will read. So this is an example. We can avoid the interference by employing the aluminum line at this wavelength. So unless you understand the spectrum, okay, the elemental spectrum, then you can understand what I'm talking about. Okay, so please have a look at the element spectrum. Then you will understand when what we talk about the lines, what we talk about the wavelength. So therefore, line interference is seldom problem. Okay, so usually you don't have to worry about this if you have a very specific lamp just now, cathode lamp just now. Okay, but this is what we call as scattering. Okay. So particulates from combustion. So remember that we have flame. Okay, we have plasma for the atomizer, especially flames. So particulates from combustion and sample material scatter radiation. Okay, so when you burn something, you have particles scattering. So that's why I have the picture scattering here. The particulates scatter, and this will interfere with the reading because if you can understand, it's about lights bombarding the atoms or molecules. But if you have any other particulates, it will also affect the lights. And if it affect the lights, it will also affect the reading of the uh, detector. So this is the scattering from particulates that we don't want. Because it's a combustion, you might have these particulates from the combustion sample because it's like burning. So you have, if your sample is dirty, especially, you will have these issues. Scattering phenomenon is most important when concentrated solutions like titanium, zirconium, which is not really usually you have in the samples. Okay, so metal oxides with diameter larger than the incident will make scattering a real problem. So this meaning that if you are to submit sample, then you have to know about your samples, whether there is a possibility that you have a lot of metal oxides, because when they burn, they have particles and that contribute to the interference. And another one is samples containing organic materials, because if you burn organic materials, you have carbon particles. That also will contribute to scattering. Okay. So what you can do is you have blank measurement, meaning that if you are to analyze chromium, then you prepare a standard chromium sample. So this is your sample from raw material, and then you prepare also a standard sample uh, based on chromium salt. It is clean. It is not sample from environment. It's not sample from, yeah, if you're doing sample from just now, what sample? I forgot. Zubair?
My sample coconut,
Okay.
coconut fruit,
All right.
co- coconut water, and also coconut flesh.
All right. So that will be considered as raw sample. So the best you run also standard solution of the minerals that you are targeting. Okay. So to make sure that you don't have the scattering issues. This is just to be as precaution. Yeah. So this is also um, the issue of sample metrics. What does it mean is um, the the raw samples that we submit to the machines has to be clean, because but some we cannot control because it's inside the sample itself. Uh, but I think if you clean it well, filtered, and you don't have any residues like particle residues, then it should be okay. Okay. Anything that interfere with the lights will have interference issue. Okay. So sample preparation is very important. Okay. Uh, no, this is much. This is okay. And then you need to know also some background of your target elements. Okay, whether the fuel, the temperature is good enough to atomize your elements. Okay, but if they say the service provider or the machine covers all the elements that you um, trying to analyze, that should be okay. But it's just that how you prepare your samples. So make sure it is clean. This one, I'm not really good in this because this is what we call a Zeeman effect. But this is uh, usually uh, being, the supplier of the machines. Usually they take care of this, so we don't have these issues. Okay, we do not have to do calibrations or baseline correction. We don't need to do this. Okay, but this is another things that all right. That's a second. All right. This is magnetic field, but I don't think you need to worry about this. Okay, it's about the magnetic. You will have a splitting effect, but we don't want to discuss about this. Okay, right? So the splitting effect is due to magnetic field. That's why we call it Zeeman effect. So I don't want to discuss this. So let's discuss chemical interference. Just now is uh, different types of interference. Concentration measurements are usually determined from working curve after calibrating the instrument with standards of known concentration. So you have to know about doing calibrations, meaning that before you can run your raw samples, you have to prepare a series of standard solution, means that a clean solution prepared from the actual salts of the minerals. Uh, but you have to know the 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 range. Are you working with low range or are you working with high concentrated range? Okay, so that has to be from literature review. So let's say you are doing what elements are you analyzing from the coconut water? Potassium or
Yeah, potassium, calcium, magnesium.
so you have to get used to what we call as uh, calibration technique. Okay, so I do teach calibration technique, but I don't teach it. I don't teach that inside this topic. But you have to familiarize yourself with a calibration technique. Yeah? So let's say you want to analyze potassium in coconut water. So before you do that, you have to prepare a standard solutions from potassium salt with a series of concentration to build the calibration. Okay, so means that you just run a standard solution of potassium prepared from the salt, and then after that you run your coconut water. But in order to establish a good calibration plot, you have to know at least the range of potassium that will be in the coconut water, if it is a high range or a low range. Because if you are preparing a calibration, you cannot cover everything. You have to cover a certain part that is uh, proportional or will be what we call that is covered under Beer's law. That okay, let me if we have it. Uh, Are you familiar with calibration plot, Zubair? Have you done calibration before?
Last time, Prof, I have done calibration
Ah,
for a spectrophotometer.
the
Is it the same?
yeah, the same. Mm.
Okay, I'm
But
familiar with that.
okay, but it has to be linear form, eh?
Yes.
Because according to Beer's law, which I don't, yeah, I don't teach here. Okay, I will teach you
Mm.
this one. I don't have the slide here.
So
the
the
the linear part only for certain range of concentration. So you have to know which one is linear. Uh, okay,
okay,
so you have to check first whether you have
okay,
a linear concentration. Let's say from 2 ppm to uh, 50 ppm is linear. Beyond that is no longer linear
mhm,
because
okay,
calibration only works with linear. Yeah.
okay,
All
okay,
right. Okay. So I think right. So let's go back to the chemical interference. Okay. So the calibration is very important to prevent any bias. Any reagents that are added to reduce chemicals should be added to the okay. This one is how you prepare the calibrations. Uh, Okay, I don't have the slides here, but I can share you the slides on how to prepare the calibration. Formation of compound of low volatility. Some salts have inherently low volatility. Uh, Low volatility meaning that it is difficult to make it into gas. So this is how we make it more efficient is by increasing temperature. That's why what we call as release agent. So I don't know whether they have it, but usually if the machines in the manual saying that you can analyze this element at certain concentration, then it's good to go. You have to check. Yeah. So this is about calcium. Okay, this is an example of how to handle calcium. So I don't have really hands-on experience on this because I usually submit the samples and the reading is good. So this is release agents, some examples of release agents to increase the volatility of the elements that you are analyzing. Okay, the another issue is ions. Okay, thereby this. Okay, so how do we avoid this? Okay, we need to put ionization suppressor. But this also usually has been settled by uh, the provider, the company who provide the machines. Because if you read the manual, they have done a lot of innovation, so you don't have to worry about this. But this is all theoretical, meaning that there is a possibility if we have more ions, and the one that we are targeting is atoms, but sometimes because of the energy levels, it converts into ions, then this will give us a wrong reading. Okay, because we're supposed to have atom spectroscopy. So by adding ionization suppressor, this will reduce the number of ions, which give the interference. But as I mentioned, machine nowadays, they are well equipped and much better. So these are just some theories that might contributing to the interference. So yeah, so this is supposed to be ground state to excited state. We do not want ions. So this is the ion suppressor. Okay, so that suppress the conversion of sodium into ions. Yeah? This is how the ion suppressor works. Okay, so I think these are all right. So I'll be sharing which is from other subject that I teach on calibration methods, which is very important. There are different two types of calibration methods that you can use. I will share with you. So you can read first, and then probably next lecture you can ask me question if you need to. Is it okay, Zubair?
Yes, okay, Prof. Thank you.
So
Thank you
for the
so much.
next lecture, we will discuss about ICP. Yeah, ICP AES,
Okay.
atomic emission spectroscopy. Okay, all right. It's awkward.
Uh,
As
I,
only
I,
one student.
yes, Prof. I got two questions
Hmm.
just now.
Okay.
One, if we have a different reading from same sample, for example, you mentioned better to replicate the sample. For example, if we have three replication and three different value, for example, 20, 23, and 15, can we discard 15 because it is very far from two other reading
Okay. Because
to,
yeah. Okay. Continue. Continue first.
to reduce the error? We can do this?
Okay, because I'm teaching what we call as statistical in analytical chemistry. So, in statistical and analytical chemistry, before you can remove outliers, the data, this is what we call as suspected outliers. You have to do a statistical test called Q test. You can just Google Q test. Okay, it's quite simple. If you do the Q test, it's just calculation. You can use Excel. Excel now you can download Toolbox, which can help you with all statistical gadgets, Q test, T test, F test. Okay, and this will tell you whether the suspicious data outliers is you need to remove or you have to include that in. So that's the principle. But sometimes students just remove because if you have three data, you can get standard deviation. But if you have only two data, you cannot calculate standard deviation. Minimum is three. Okay. So when we do analytical, regardless in your case, chemistry or agriculture, is always about analysis. Statistical methods is very important. So you need to have error bars, you need to have standard deviation. And then if you are comparing with standard methods, you have to do t-test, f-test. Okay. So analysis has to be in that manner.
Okay, thank you, Prof.
Right. So please do familiarize yourself with statistics.
Okay, okay,
Okay.
inshallah.
All right.
One more question, Prof.
Hmm.
Uh, for the low volatility interference, can we can be the concentration of sample a problem? Maybe sample is in high concentrated level.
Okay. I don't get the first when you mention about. Can you repeat the question?
Okay,
Uh,
if our sample is very concentrated,
mm,
can it cause low volatility
yeah.
to make interference?
Mm. Uh, I I I'm not so sure because that depends on if you analyze and then you think that the data is not really good, then there's something wrong. So what what I'm going to say is you need to know some background of your samples. Meaning that from your reading, from your literature, you should know some basic range before you can do the calibration. Because as I mentioned, you cannot prepare the standard samples from very low to very high because the linear range only works at certain range. If you want to read that, you have to read Beer's law. Okay. If you are working with coconut samples and if you like you probably you need to run it first, and then if you find that the reading is not good, then you have to do some dilution. You have to do
Okay.
some dilution. So when you do analysis, it's not always everything is good in one shot. You have to do a few analysis. Okay,
Yes.
right? So yeah,
Okay.
my answer,
Okay.
yes. High concentration will affect the linearity of the calibration plot.
Okay. Thank you, Prof.
All right.
Thank you.
Okay, so see you next week.
Okay, Prof. Thank you so much. See you.